So to solve this example last week, so in order to just make a reminder, please please write a relational algebra expression that I'm sure that everyone has practiced this and everyone has exercised. Write a simple relational algebra expression to find out all the students that are not taking 3 courses but are taking at least 2 courses. Okay? 2 different courses. So just write this query and let's see what's going on. The students who are taking at least 2 courses but not taking 3 courses. 3 different courses. I guess in 1 minute you can easily solve this problem. So, how do you solve this problem? Any guess? First, just give hints to your friend at least.
We'll take 3 tables like that.
What?
3 tables, transcript table normal, and again transcript table with the course code 2, sum to grade 2, and transcript table 3 with course code 3, sum 3 and grade 3. We add these 3, and we have 3 courses. Then we can eliminate the person. Less than 3 courses we can.
Awesome. Write it down. Perfect. The solution, your friend told the solution. Just write down the expression. The expression is a bit long, but do it in 1 minute. You write the solution also. I'm expecting you to do the first one, right? Just write it. So the answer is very easy. So you got the answer, right? How many people solved this? just need to get feedback from the class. How many people successfully wrote this? Yes. This 1, 2, 3, 4, 5. I'm expecting more people. Okay, so let me explain what's the solution in order to move faster. So, in the previous answer, in the previous question, we were expected to extract the name of all of the students who are at least taking 2 courses. Okay, but from these students, we are not interested in those students who are taking at least 3 courses. Okay, we just need people taking at least 2 courses. Therefore, I'm writing the second part. I'm using a set minus over here, and I'm writing the second part as follows. I'm projecting the student ID because previous table has a student ID, and we cannot have more columns because why? Why? What? No. We cannot have more than one column, and the column should be what?
Duplication is there.
No. No. It's very simple. We cannot have more than here. I project just a student ID. Why?
Foreign.
No. It doesn't relate it to the current design of the table. One more important reason. I'm using a set operation. The 2 tables, the 2 relationship. One is up there, and the other one is down there. They should be set compatible. They should be union compatible. Okay. So if I select 2 columns, then the tuples from this relationship will be different from that one. Then how can I do the set difference?
But
Okay.
without the difference also, this gives the answer, right?
Which one? No. I'm interested in students who are taking at least 2 courses, but not taking 3 courses. So I need to set difference. The first one is computing all of the students taking at least 2, 3, 4, 5 courses. Okay. The second relationship I'm writing here is actually selecting all of the students taking at least 3 courses. Okay. So the same as what we did for 2 courses. We are projecting a student ID. We have a select on transcript 1, transcript 2, and transcript 3. Okay. There are three replications of transcripts.
It's like less than 3, Professor, or 2 and
Only
not
2.
3?
Only 2.
Only 2.
Yes. So then we can see over here that similar what we did up there, we are renaming the column except the student ID. All of the columns in a different name. Okay. Therefore, the attributes of these 3 relationships from the point of the name of the attributes will be different except the student ID. Okay, then the join will happen on the student ID. It's a natural join. Okay, but the rows will be different. Okay, if the student is taking 3 different courses, there will be at least for that student there will be at least a row with 3 different course codes, completely different course code. So this expression, course code 1, course code is not equal to course code 2, and course code 2 is not equal to course code 3, and course code 3 is not equal to course code. This means that there is a row at least 3 different course codes in that row. Okay? None of them are equal to each other. So it means that the student is taking at least 3 courses. Okay, then those will be removed. So just a quick answer. I don't want to write the question. If we want to have the students who are taking at least 2 courses, not taking 3 courses, and have take at least have take at least 4 courses or more, what will be the answer? What will be the answer?
At least 2 courses minus exactly 3 courses.
Minus exactly 3 courses is this one. And or the guy is taking more than 3 courses.
Question one more.
I'm interested in the person and in the students who are taking at least 2 courses or and not taking more than 2 courses, or the people who are taking more than 4 courses, equal or more than 4 courses,
2 courses or more than 4 courses.
equal or more than 4 courses. Yes.
Yeah. Then
Then we can
2
take a
courses
plus,
or more. 2
and
courses.
we can remove all the
Plus or union.
in.
Union. You don't have any plus. You can do union and do the same trick for the 4 courses, right?
Add.
There will be 4 copies of transcript, 4 types of renaming, and then the same trick. So this is cascaded. Okay. Everyone understood what I told you, right? Okay. So who didn't understand this problem? The answer for this problem. Is this obvious for everyone or not? Okay. So if you want to compute the set of the students who are taking 2 courses or 4 and more courses, how can we compute this one? One part of the answer will be the same as what we wrote over here. Okay? The same as what we wrote over here. The rest of the answer will be, as your friend mentioned, it can be a union of the students who are taking 4 or more courses. To compute the students who are taking 4 or more courses, we are doing the same trick. Here, in order to compute the students who are taking at least 3 courses, we did what we did was using transcript 3 times natural join to itself with different name of the columns. Natural join on the student ID. The rows of this table shows that the students of this table shows that the student is taking at least 3 courses. Okay? So for the 4 courses, instead of 3 joins, I should use how many joins? 4. 4 tables in the join, or 3 joins, right? If you use 2 joins, it will be 3 joins and 4 tables. Okay, so another important operator is division, basically. The goal of the division is producing the tuples in one relationship. This is including all of the tuples in another relationship, in some part of this relationship. Okay? Suppose that you have 2 relationships. One is R, the attributes are from A1 to AN, and B1 to BM. Okay? You have another relationship, the attributes are from B1 to BM. Okay? These relationships have n rows. Okay? Suppose that this relationship has k rows, k number of rows. Okay? So we are trying to extract a table or a relationship with attributes from A1 to AN, and those rows and records are showing the rows from this relationship that are including all of the information from this. So this relationship can be expressed in terms of projection, set, difference, and cross product. Let me give you a brief example. Suppose that we have a table, this is an instance of relation S, and this is an instance of relation R. Okay. R has A1 to AN, B1 to BM. S, B1 to BM. Okay? So here, M and N, both of them are 1, right? We have one column that is not included in the relation S, and relation S has only one column. Okay? So we have relation S. This table has 3 rows, A, B, C. Okay. So we would like to extract a relationship with just only one attribute, which is A. And whatever it appears in the A has in the B part in relation R has all of the records this guy has. For example, here 2 should be included because it has A, B, and C. But 1 cannot be included. Why? There is no C in relation R for a attribute A. 1. Okay? So is that clear or not?
Yes.
Okay. So here is one example. We want to list the IDs of the students who has all the courses that are not taught in the spring 2000. Okay? In order to solve a problem like this, or in order to express a relation or algebra expression to solve or represent this relationship, we need to first determine what is the numerator and what is the denominator of this division. Numerator and denominator should be 2 different relationships, okay? Numerator should have columns that are included in denominator, right? So the number of columns in the denominator should appear over there as well. And also it has to have some columns more. Here we are interested in the student ID. So we have the student ID. Okay. So we have the student ID. First of all, let's find the denominator. It says that these IDs of a student who have passed all courses that were taught in spring 2000. So definitely in the denominator of the division, we have to have a table showing all of the courses taught in that semester. Okay? So how do we get that? Suppose that we have a table teaching, and in that table we can filter out all of the rows with semester is equal to S2000. Okay, now in the denominator of part of the division, we have this set, all of the courses. Okay, so in the numerator of the division, we are computing a table or a relationship that are mapping the student ID to course code. And the grade should be the grade shouldn't be F. The person should pass it. So two tables, and for the result, the result of the division of this table, this relationship to this relationship. Okay, now it looks like we need one more example. Okay, so consider the same relationship here, and we had for professors and registration and student IDs, and find out professors who taught to every student. Professor who taught to every student. Okay, now let me running. Okay, so suppose that you have a table professor. Yes, prof ID, name, contact code. have a table of student. Okay, suppose that you have these four relationships. Now compute the professors who taught, who have taught to all the students. I suggest that to start from the bottom of denominators. To solve this, any volunteer to solve this problem? Face. Bring this one and this face. You want to face. You.
Are you using this symbol?
So this is the denominator part. So now the first part. What should I do? The name of the professors who talk to everyone. There should be a division over here, definitely. and
Professor ID, project professor ID,
project professor ID and
courses,
Select the teach
students,
a student ID, because that one is just, remember that the condition was here, column B1 to Bn is exactly repeated in our S, right? The column B1 to Bn, here B1 to Bm. Okay, therefore, a student ID should be included here. Then, okay,
courses,
courses or teaching?
teaching,
Teaching. Teaching. Natural joint with transfer.
select teaching course code is equal to transfer.
What? You don't need to select because it's a natural joint. And student ID, course ID, course code is here similar and semi-similar.
We have to
If
find
a professor,
we have to print the name of the professor.
okay, now this is the third part. What's the third part? Here, I should do
Join with professor.
professor.
And project name.
So simple, right?
Can you explain with an example?
What?
Can you explain with some example?
Explain the example.
With an
With the
example.
table.
Some table.
I watch it.
Yeah.
Have to write the table tomorrow. Okay, so let's see. Suppose that we have two professors over here.
This one is what we'll check the condition in the paper. Primary condition. Suppose you are checking what the course goes and the course code and getting all the details of that. This is the final projection. Projection. What you want to see. This is select. I think you
Suppose that we have
need it from
three professors over here.
Don't try for it's not flexible. It's very
This is also moving right.
Also, sorry.
Sometimes I used to curse, see the video now. Sometimes Jesus they don't move it on the side. I used to curse.
ID 1, 2, 3 is also Michael. Department code for these two are CS and this is mathematics. Okay, this is a table for this one. Suppose that we have students. Student ID. One, two, three, four. There's some address for this. Okay, so this is the student table. We have a teaching table. Professor ID, course code, and semester. And then suppose that Professor Mahmoud is teaching in fall 2016, spring 2016, spring 2017. 15 is switching CS 5 14 CS 5 41 CS 5 40. Okay, so let me erase this part, or let me write this part. This part. Suppose that we have this transcript table. Okay, so 1, 2, 3, 4, 5. Okay, so what is the result of these 4 tables? What is the result of? We have this number of students, 5 students. Suppose that we have 5 students and 3 professors, Asif, Julius, and Michael. Okay.
Awesome.
Okay. So Asif is why? Because you can see that every student has at least one course with Professor Asif. Okay. So if you want to compute first, all of the students will be 1, 2, 3, 4. The student that is there 1, 2, 3, 4. Okay. This part. Now compute this part. Teaching natural journal transcript. This is teaching and this is transcript. It shows that this. If I want to use another color of marker. Okay, then the result of this one will be table relationship with some more column where there is a profiling over here and some other columns over here with respect to the name of the professor, name and also department they call. Okay, this is Professor Mahmoud.
With the transcript and teaching, we will not get the name and department.
What?
With
This is
transcript and teaching, actually,
Transcript and teaching. Transcript, teaching.
how can the professor name will
Okay, it's join, right?
how will it join us?
It's a join. The name of the other columns will be added, right? Okay, then Professor Mahmoud will be here. Professor Mahmoud, Professor Julius will be here. Professor Mahmoud, Professor Mahmoud, Professor Mahmoud, Professor Mahmoud and Asif. All of them are sorry, the second one is Julius. Okay, the rest is awesome. Okay, so here you can see that Professor Asif is teaching to every student, because if you complete the division, you will see that Professor Asif has a course as a row at least for each of those students. Okay, then this will be Professor. The rest of this table will be Professor ID, and then Professor ID of the Professor Mahmoud. Then probably even we don't need to. We can make it simpler. How? We can make it simpler. This is correct, but we can make this relationship simpler. How? We can include the name of the professor over here, right? Because this relationship can have the name of the relationship as well. Okay? Then we remove. Oh,
I have a
sorry.
doubt.
There is no name. Sorry. I was confused. The professor, the teacher doesn't have any name in it, so this is not name. This is just course code and semester. Okay, just right. This is just professor ID will be added to this to compute this one, and then we'll join it. You're right. That's correct. Okay, so here is an example of the relationships. Okay, we have to go very faster. Then you're complaining that I'm talking fast, but you're asking for examples that are taking time. Okay, I got this complaint from the Professor Mahmoud told me that the students are telling him that I'm talking very fast, so I have to talk a bit slowly. Now, I would like to, from now on we will switch to SQL language. I hope that I can cover the SQL language today. If we cannot, we briefly next week we'll continue on this. Hold on, Tuesday will be off, and there will be no classes on Tuesday. So I talked to Professor Mahmoud, and because we are far behind our schedule, I would like to have a makeup class for you. I was planning to execute some samples and examples in Oracle for you, but I realized that I don't have time to do that in the class. So together with distance learning students, I will record some screenshots from in my office and put the video as the makeup class. If we are still far behind of the schedule, then we will schedule makeup class. Okay, consider these 6 tables. From now on, we'll work with these 6 tables. So the query sublanguage of SQL. We are starting with query sublanguage of SQL. So SQL is a declarative. We talked about this. SQL is a declarative programming language where we just express and specify what kind of data we want to extract from the database. Okay, that's it. it doesn't explain how this data will be extracted. Okay? The simplest instruction of the SQL query sublanguage is select. The format is like this. Select the column from the table course, name the table course C over here, and then here we can write a where condition. There is a where clause over here which specifies which rows should be selected. The select language, the select instruction is equivalent to this form of relational algebra expression. So now time to consider join queries. Suppose that we have two tables in the from clause, okay? Table course and table teaching. So if we have two tables, by default, the result of the select will be the Cartesian product of these two tables, these two relationships. Okay? Now, in order to compute and consider the natural join, we have to match those columns with the same name manually. As you see here, for example, we have course C and teaching table as T. Okay? So, as you may remember, in order to natural join these two tables, they only attribute, their shading is what? Was course code and what was it, teaching? Yes. Course code and teaching. The only attribute they are shading is course code, okay? So, here we put this condition on the Cartesian product in order to make this join as a natural join. Okay? Course code is equal to C course code is equal to T course code, and also the rest of the where clause is specifying additional conditions if you want to. Additional conditions we want to the rest of the rows satisfy. Is that clear? Clear or not? Okay. Okay, so here is the join condition. Course code is equal to T course code, as I mentioned. And also, couple variables are clarify meaning. We are listing just the course name, and the selection condition is here. And this query is equivalent to one of those subsequent, one of those relational algebra expressions. So,
then where we are giving the condition of course code, C course code is equal to T dot course code in their relations. We are
okay,
giving semester is equal to S2.
this is a natural join. This is not a Cartesian product. If it was a Cartesian product, you had to have this condition, this equal condition over there. But since it is a natural join, by automatically it matches the columns with the same name. Okay, and the course code was similar. But in SQL, we don't have this option. We have to do it manually. We have to specify to that Cartesian product that these two columns should be similar. Okay? So, suppose that consider these two. I want to give you something about the. I want to give you some hint about the computations of and processing queries. we have these two relational algebra expressions. Suppose that in table teaching, just 10% of the records are corresponding to semester string 2000. Just 10%. Okay? And also, suppose that course table has 2000 rows and table teaching has 3000 rows. Okay? So let's have some estimation on the number of the rows we are computing in each of these parts of relational algebra. Okay, so if we do this select over here, how many rows will be here?
6 million.
10% of 3000. 10% of 3000 is 300, right? The number of rows here is 300. How many rows over here?
2000.
2000. Okay, now let's consider this one. How many rows over here?
3000.
How many rows over here? 2000. And we will select. Okay, so 3000 and 2000. Okay, give a rough estimation about the number of the number of the records of these two tables. Give a rough estimation. Suppose that 300 of this one is coming out. Let's say. Okay, so we don't need this estimation for now. So, which of these computation is faster? Do you think?
First one.
First. Why?
Because we are doing natural join of 2000 to
Natural
300.
join is done after the selection, so the number of joins will be less. Number of completion will be less.
Exactly, because in order to compute this one, we have to have, when we are computing in a natural join, when we are trying to respond to the natural join query, what we are doing is we are doing the Cartesian product and we are matching each row by each row. Therefore, in this relationship, we have to consider 2000 multiplied to 300 rows. But the lower one, the bottom one, how many rows we should consider?
6 million.
It is 6 million rows. The up there is
600,000.
600,000. Means that this query will be more efficient. This relational algebra will be more efficient. So now you understand one of the differences between relational algebra and SQL query. What is the difference? Relational algebra shows how to answer this query. Relational algebra also shows the sequence of operations. Therefore, relational algebra is some sort of procedural language. It represents how this query will be answered. But in the select query, we don't have any idea how this answer will be computed. Right?
But we can give nested SQL queries, right?
The nested SQL query changes the relational algebra and it makes it faster. That's all. Yes.
So the SQL query is equivalent to which one of the?
Both of them. SQL query is equivalent to both of them. And both of them are returning the same result, but with different approaches. Okay, so self-join queries. Here, for example, you want to, you remember the example we had for transcript? If you want to write that example, you can write it right now by yourself. Okay, so I don't want to give you classwork, but I think that I should give you some classwork. Okay, just write the query that we did for the transcript. Write a query to find out the students who are taking at least 2 courses. SQL query. We had this select query, same select query. We also can write another equivalent for this select query. How we can write this correspondence?
Another select sequence.
We just simply transform the join with the Cartesian product and added this join condition. Right? Correct? So this is how we can write it. The previous slide, the two expressions, they are using this convention of join, natural join. But we knew that natural join is implemented with the Cartesian product, where the condition is enforced on the Cartesian product. Okay? Okay, so this is the simplest evaluation algorithm for select. Basically, as I told, relational algebra is showing the procedural language, which is showing how these queries are evaluated. So this is also a self-join query, as we mentioned. In the select by itself doesn't eliminate duplicates. Why? The first answer is maybe someone wants to see how many duplicates it has. But the correct answer is that removing duplicates from a relationship is very expensive. You have to first sort it, and the fastest sort algorithm we have is n log n, and then remove and go over it with a linear search. Okay? Therefore, in order to remove duplicate rows, if we are interested in removing the duplicate rows, we have to put this word distinct over here, which eliminates duplicate rows. Okay, so now we can also in the select part and also in the where part we can compose interesting string with this concatenate the string operator. Okay, so in the where part of the SQL query, we also can have comparison between the strings, which is doing the comparison based on lexical order. How many columns this select will have? This is one column, yes, exactly. And the name of the column will be? Name and but we are composing in a string. This query cannot be represented in relational algebra by itself, in this format. Okay, so and set operations are also used when the tables are union compatible. We have union except, which is equivalent to set difference, and intersect, which is intersect the two sets. For example, if you want to find out professors in the CS department and all professors who taught CS courses, first you can compute all of the professors who taught courses from CS courses, and then select them with all the professors from CS department, and then union with this result. This is obvious, right? Is this obvious? There are two sets union. Nested queries. Your friend before pointed to this query. We can have nested queries. Nested queries are those queries that are computed in the where clause of another select query. Okay? So here, in order to compute this query, what will happen is basically this select query will be computed, and then based on the computation of this select query, the where clause will be evaluated, and then the results will be computed and returned to the top. There are some important points over here. What are the points?
Not
Not in is one operator that removing, considering. The other important part is the hierarchies of variables. Variables, the name of the tables are coming down from the upper level query to lower level query. Okay? For example, here you can see that we are selecting professor name and department name from professor and department, where professor ID is in this. You know that this is comments, right? These are comments, right? Two dashes starting a sentence or a phrase until to the end of the line. That will be comments. Okay, so PID, and these are two tables in this query. Okay. Here, PID should be in this subquery. Okay. So here you can realize that this D, table D, is not in the from clause of this select query. Consider the select query. This D is not here. Okay. So what happens is basically the table D here is considered as a global variable to the rest of the queries nested inside. So this query can see the table D and can recognize the table D and its column and its relations. But this table cannot manipulate these columns. These are not, the columns of this table is not going up there. The only place these columns can be used is in a where clause. So these are explanation of what we saw over there, top variables. Okay, so it looks like we need to stop right now. So we will continue next Thursday. I will also send you the instruction.